Okay, this is the second lecture, lecture number 2. Okay, chapter 1, general principles. Yeah, I would like to introduce the concept of stability. If you get this kind of curve, concave curve, then there is some ball here. So if you touch this ball, and then if balls go and this ball come back, it simulate stable equilibrium. The status is stable, and then this ball is stay on point, so we call it equilibrium. Another one, this one is plane surface, there is a ball again. So if somebody touch this ball a little bit, then this ball has a new position somewhere here, move to new position. But this ball does not move anymore, okay? So this ball stay one position, so we call it the equilibrium. This ball, if we touch it, this ball move a little bit, so we call it neutral equilibrium. This is convex curve. Okay, there is a ball here, and then if somebody touch this ball go away. This ball cannot come back. The status of this ball is unstable, so we call it unstable equilibrium. This one is stable equilibrium, this is neutral equilibrium, and unstable equilibrium. So I already explained this one. So if you consider this column subjected to some axial force P here, we consider the ideal column. Ideal column means this member is perfectly straight, and then this loading also applied at the center of the column, then we call it perfect column. If we apply the loading, if this loading is small, then there is no displacement, the loading goes up. But this loading reach a specific point, then this column suddenly buckle like that. So lateral displacement suddenly increase like this. This curve can be seen in perfect column. Okay, so from here up to this PCR, we call it fundamental pass. And then this point, this column buckle, we call this point as buckle node or bifurcation point, or stability limit point. From this point, the stable state and unstable state, okay, it bifurcate. So we call it bifurcation point. It goes up or buckle like this. If the structure, this member is a fundamental path somewhere here, then in our some FM analysis, the stiffness matrix is positive definite. Okay, this bifurcation point, tangent stiffness equal to 0. Okay, so the lateral displacement suddenly occur like this. This path is called post-buckling path. Path after buckling, fundamental path, post-buckling path. Look at here. Let's assuming the axial load somewhere here. Somebody touch this column, then this column might move just a little bit, and then come to original point. So it simulates like this. Concave curve and ball here, touch ball, and then ball move a little bit and come back the original position. It simulates this range. Okay, if we consider some perfect column, there is no some vibration, no wind, then this load might be increased like this without any buckling, because this column is perfectly straight and applied concentric load. There is no ambient vibration, some wind. Then this column can sustain more load above this PCR. Let's assume this point. Then if somebody touch this column, what happens? Suddenly buckle like that. Yeah, it looks like this ball go away. Okay, goes away if somebody touch this ball. It is same phenomenon. Yeah, that is very typical perfect column. Okay, so this column, if we get the result PCR, then PCR equal pi square EI over S square. You already learned from the undergraduate study. We also learn this course also, how to drive this one. Yeah, if the column is very slender column, there is no yielding in any part at a section, then PCR pi square EI over n square. That is this point. Okay, it is called Euler buckling load. Yeah. Let's move to type of system. And perfect system, we can get PCR. Okay, as I mentioned just before, this PCR. In imperfect system, there is no PCR. Imperfect system means that column has original deformation like this before axial force applies. So originally not straight column. So in that case, we call it imperfect system. In that case, load apply, load increase a little bit, then this displacement increase. Okay, can you imagine? So if you draw this curve P delta, this we have original deformation delta 0. Okay, the load increase, then displacement increase, then we can get this curve. Okay, yeah, this imperfect system. This imperfect system does not have any PCR. This PCR occurs only perfect system. Here, in perfect system, we can do bifurcation analysis. Okay, this point is a bifurcation point. This way or that way. Bifurcation point. Or eigenvalue analysis. Eigenvalue means unique value. What is unique? PCR is unique. So eigenvalue analysis. Suddenly buckle. Imperfect system, this kind of analysis is called load deflection analysis, because as load increase, deflection increase. Load deflection analysis. So this ideally straight column is not realistic. Okay, so realistic column is imperfect system, in fact. So I would like to introduce type of analysis. In order to solve this stability problem, there are two ways of analysis. One is equilibrium method. Another one is energy method. If we use the equilibrium method, we can get PCR, buckling mode, magnitude of deflection. In this method, we use the equilibrium equation. Energy approach use total energy concept. When we use the energy approach, we can get the all of the solution. Additionally, this energy method can get the nature of stability. I can show some example. Okay, then you can understand clearly. Okay. Another one is a type of deflection. There are two different types. Small deflection and large deflection. If we assume small deflection, we can get PCR buckling mode. If we assume large deflection, we can get PCR buckling mode and magnitude of deflection. If we assume the small deflection, sine theta equals theta, cosine theta equals 1. If the theta is very small, sine theta is equal to theta, cosine theta equal to 1, right? If theta equal not that small, then sine theta just keep sine theta. Cosine theta maintain cosine theta. Okay? Based on the knowledge so far, I would like to show an example. Example problem 1. Rigid bar. This is rigid bar with rotational spring here. How many degree of freedom in this problem? Just one rotational degree of freedom at one point. So this is a 1 degree of freedom system. Okay, it is not realistic. But in order to understand the basic concept more clearly, I'd like to show very simple example. Okay, for this specific problem, let's assume perfect system. The perfect system is there is no original deformation, and then assume small deflection. Under this assumption, in order to get the PCR, we assume this place P applied here. If it rotates with theta, then this length is L cosine theta, right? This vertical displacement is L sine theta. Okay, and then this rotational spring is Ks and theta. Ks times rotational angle, then this is moment, right? So we assuming small deflection problem. So sine theta equals theta, right? Cosine theta equal 1, okay? We can use equilibrium approach or energy approach. I'll show both equilibrium approach first. So if you take the equilibrium from this point, let's say this point, this is, we have the moment here, Ks theta, right? And then we have the moment P L sine theta, right? It is the opposite counterclockwise direction, so it is minus, okay? Equal to 0, right? So we assuming the small deflection problem. So sine theta equals theta, right? So Ks theta minus PL sine theta equals theta, okay? Equal to 0, yeah. So in order to satisfy this equation, if theta equals 0, then this equation satisfies, right? So if theta equals 0, that means this vertical axis, then we cannot get PCR through this solution. So we call it trivial solution. So another way to satisfy this equation equal what? Ks equal PL, right? That satisfies this equation. This P equal Ks over L, right? This P equal PCR, this point, okay? So we can get this PCR, okay? So another way to solve this problem is energy approach. Okay? So energy, we have two different energy, strain energy and potential energy. Strain energy can be calculated like this. This is moment times theta is equal energy. So if we draw the moment theta relationship, moment equal Ks theta, right? This is theta. If theta increase, and the moment increase and increase. So they have some linear relationship. Some strain energy can be calculated. This lower triangular area. This area, as you see, 1 over 2. Okay, Ks theta and this theta. This area is strain energy. Another energy is potential energy. As you see here, original location of P is somewhere is L, L position. As this bar rotate like that, this P move, okay, left hand side. How much? Yeah, this much, okay, this distance from here to here, this distance. So the potential energy equal P times the movement. Movement is L minus L cosine theta. It is the movement. The reason of minus is this P lose his energy, so it's minus. This spring gain some strain energy, so it is plus. So strain energy is from this the spring. Okay. Potential energy is from this P. So energy reduced, so minus. Yeah. So the total energy equal pi equal strain energy and potential energy. U plus V. So this one and this one. So we have to find the equilibrium position. Then we have to have the stationary value. So mathematically, we take the derivative of total energy regarding this rotational angle. Derivative, then we get from this equation here Ks theta, okay? And then PL eliminate cosine theta minus sine theta, right? Take a derivative, then minus sine theta. Then we can get this equation. We are assuming this problem is a small deflection problem. So sine theta equal theta, right? Okay, so Ks theta, PL theta. So Ks equal PL. So P equal PCR equal Ks over L. We get the same result with when we use the equilibrium approach. So next problem, we assume perfect system, but assume large deflection problem. So in large deflection problem, what happened? Sine theta equal sine theta, right? cosine theta equal cosine theta. That is large deflection. Yeah, so we handle perfect system. That means we can get PCR. Yeah, so the equilibrium equation, this one, okay? It is same. K theta minus PL sine theta equal 0. But in small deflection problem, sine theta equals theta, right? This is a large deflection problem. Sine theta, we just keep sine theta equal 0. So this P equal Ks theta over L sine theta, right? So this large deflection problem, we can get the curve because deflection is large like this, okay? We can get the curve in this range. I mean the small deflection assuming, then we can get just PCR. Large deflection, we can get the post-buckling pass when we consider the large deflection. So you can get this post-buckling pass. So if you draw this one, theta 0, pi over 4, pi over 2, input here, you can get this curve. This is post-buckling pass. Yeah, from this curve, we know in order to make more deformation, this system need more load. Okay, more load. So curve like that. So we call it stable post-buckling pass. If post-buckling pass like that, then we call it unstable post-buckling pass. So this is a fundamental pass, post-buckling pass. If we do perfect system and large deflection problem. Okay. If we use the energy approach, this is the first derivative from this one. This energy approach, if you see this one. But in large deflection problem, we just keep sine theta equals theta. Yeah, so we can get the same result with this one from this equation, P equal like that. We call it post-buckling pass. If we do the second derivative, then from here, second derivative, yeah, then we can get Ks here. PL sine theta is cosine theta. Then what is P? Input this P into here. Yeah, Ks theta L sine theta here. Okay. L delete Ks 1 minus cosine theta move to in downward, then tangent theta theta. That is the equation. Then do you know theta over tangent theta is always less than 1. Here the theta is radian value, so this is always less than 1. That means this term is greater than 0. This second derivative value is greater than 0, means post-buckling pass always stable. More load is required to obtain more deflection. That means the system stable in post-buckling pass. So if we use the energy approach, we can get the additional information. What is that? We can get the stability of the post-buckling pass. I mean the stable or unstable. We can get some nature, characteristic of post-buckling pass. Last one is we assume the imperfect system and large deflection. Imperfect means before apply the load, this system has original some deformation, theta 0. And then apply the loading here, P, okay? And then deform up to theta like that. After loading apply, this system deform, rotate from here to here. But for the calculation, we just this one is theta 0 from here to here theta. So the moment occur with the magnitude of Ks theta minus theta 0 because it rotate from here to here theta minus theta 0 after load apply. So this dotted line is the original the location. So this the horizontal project length is L cosine this theta 0. Okay, this one is L cosine theta, right? Yeah. From here to here, L sine theta, right? Yeah. From here to here, L sine theta minus this one, okay? Sine theta 0. That is geometry. So let's use the equilibrium approach. So moment occur like this. So Ks theta minus theta 0, right? Yeah. And then if we take the moment here, P L sine theta, right? Minus equal 0. Okay. From this equation, we can get P equal Ks, theta 0. If we move this part, the L sin theta. We call it equilibrium path. Okay, it is not post-buckling path because this is imperfect system. There is no buckling, so we cannot call post-buckling path imperfect system. So we call it equilibrium path. If we use energy approach, strain energy is 1/2 Ks, then the rotating angle, potential energy minus PL, this distance and this distance, right? So cosine theta 0 minus cosine theta. Okay. Total energy is this one. Okay. Just add together. Take the derivative, then we can get this term. This term become to this one. This term, this is constant, so it disappears, and then cosine sine equals 0. You have the same result with this one when you use the equilibrium path. Okay? And let's look at some nature of stability. That means the equilibrium path is stable or unstable. So in order to get the nature of stability, we have to do the second derivative. Then Ks minus PL cosine theta. This P equal this one. Plug in this P value. Then you can get Ks, yeah, like that. LL delete cosine downward and then tangent theta. If you compare theta tangent theta is always greater than theta. Okay. Then if one side you take the minus theta 0, that means even tangent theta is greater than this value. Okay. Yeah. So if you move the downward like that, then you can get theta 0 tangent theta equal less than 1. Now from here, this term is what? Less than 1. Then total value is what? Greater than 0, right? Second derivative value is greater than 0. That means stable. We are dealing with a large deflection problem. This is not post-buckling, right? What? Equilibrium path, right? Equilibrium path is stable. This is equilibrium path. Imperfect system. Yeah. Large deflection problem, right? If you plug in theta, if theta equals 0.1 radian, then you get this path. Theta equals 0.3, get this path. Perfect system, previously you get this PCR. Perfect system and large deflection problem, you can get this post-buckling path, right? Yeah, this is a summary of some up to some calculation. Okay, see you next time. Bye, everybody.